happen if we vary the different aspect ratio of the block. Okay? So this is a fairly simple problem, but surprisingly, there's no solution for any one of them if you want to do it carefully. Okay? So how can such a simple problem have no solution? Well, I'm going to go through the details, and then we go from to understand that. So case 1 is very simple. This dimension is very long, and it's much bigger than this dimension. And then the thickness direction D is even smaller, so it's kind of like a thin, long sheet. That would be most of what you do when you do a tension test of a soft material, right? Okay? So this is a loading direction. So that would be kind of a tension test. The second case is when the two dimensions are comparable, but the thickness dimension is small, so that will be a plate-like material. The third direction is what a lot of us do when we do a pure shear test, right? Sometimes if you do fracture mechanics, you'll put a crack in here, and you clamp this and load it in up and down in the vertical direction. Okay, right? So we'll think about how each one of this problem and how we can solve them approximately. Okay. Okay. So case 1. Okay, right? The out of plane stress is approximately 0 because the plate is very thin compared with all the other dimensions. So D is very small. So we take the approximation of plane stress. That means the out of plane stress is identically 0. Okay, which is a good approximation. Now, so this is a tension test. So we put this in a stiff machine, right? Clamped it, right? And away from the clamp, we sometimes call it the gauge length. Okay. Now, but when you clamp a specimen, if your clamp is any good, your specimen is not going to be able to move, right? Okay. So when you move this up, this guy here cannot contract at all. And we all know that if the middle part, or as long as you are away from the edge, the middle part is going to contract, right? Okay. So if you use this test, you can never generate a truly homogeneous state of strain and stress because this guy here contracts, right? Okay. So when you do the analysis, you're just basically saying that forget about this. We're just going to make this infinitely long, okay? Forget about the edge effect, okay? And we now assume that the material has a simple stretch independent of position because obviously, right, because it's infinite, every place looks identical. So the stretch ratio in this direction too is lambda, and the other two directions, I assuming incompressibility, is 1 over square root of lambda, so that if I multiply this, the determinant is 1. So and we already solved this problem last time, that the nominal stress is basically the shear modulus, the small strain shear modulus, times this factor, okay? So, and for very small strain, if lambda is very close to 1, then this is equal to the Young's modulus times the extension of the bar, right? So this is something that you all know, okay? Now, so let's think about it a little bit more, right? So why do we want the bar to be long? How long is long, okay, right? So, and what actually happened at the edge? Well, the edge effects are important, right? Because if you have a very short bar or if you have a very sharp edge, usually there's a huge stress concentration there, like this window, right? Okay, right? There's a very sharp edge at the window. Now, you notice that when you go on your plane, the windows does not have a sharp edge, right? It's rounded. Well, because if they put a sharp edge there, I wouldn't board the plane. Okay. All right. Okay. So, so one thing, okay, so this bound, so let's look at it, okay? So this is an exaggerated view of the actual deformation. If you do a calculation, you will find that because this edge is fixed, so it cannot come in. So the material would like to come in here, right? It wants to shrink in the middle, so it will look something like this, right? Okay. And so this is the, so in here, I'm drawing a middle line here. So this is this middle line here, right? Okay. And so that's a mid-plane of symmetry. So on that plane of symmetry, there cannot be any shear stresses in here, right? Because it's a plane of symmetry. Okay. Now, so one thing that we want to think about is, in order to gain insight, we really have to think about, before we do any calculations, what does the force look like? So the good idea at this point in mechanics is to draw a free body diagram. Okay? So free body diagram shows you what kind of forces are around and clear your head. Okay? So far away, we expect we have uniaxial tension, right? So this is just E times the strain. I'm doing a small strain theory right now, okay? And then we do the large deformation theory later. Okay, so now at the edge, because this guy here cannot shrink in, there's got to be horizontal shear stresses exerted on this edge to prevent it from shrinking in, right? So that makes sense. Now, but if there's a shear stress in here, what's to balance it? Well, there's got to be some normal stress on this side to balance it, even though far away from here, there's no stress at all. But without normal stress, to balance this, this guy here is not going to be in equilibrium, right? Okay. So in here, we cannot, the normal stress here is not the same as the normal stress. We don't know what it is. The only thing we know is that the net force in here has to be equal to the net force in here, right? Because there's no shear stress in here, right? Okay. So that's all we can say, right? Okay. And near the corner, we have no idea what happened near the corner, so I put a question mark there, all right? Okay. So let's look at what the calculations say, okay? So there's no exact solution for this problem. That even in linear theory, we cannot solve the problem, so we have to take a computer and do it on the computer using whatever method you like, but in here I use a finite element model, okay? So let's look at what happened on this edge, okay, right? On this symmetry line. On this symmetry line, right, far away, so here is 0, right? So 0 is here, and I'm going up, right? So far away, so this point is 0. Far away, the shear stresses is 0, which we all know. It has to be 0 on the symmetry line, so that's not surprising. Sigma 1, that is the stress in this direction, indicated by the red arrow. They are also 0, right, which is expected because that's what the uniaxial experiment theory tells us, okay, the infinite theory tells us. But in here, you can see that there is some normal stress in here, right? And it's indicated by sigma 1. That's exactly what happened, right? Okay, right where the curvature ends, the appearance of some stress in the horizontal direction, which is indicated by this blue line, right? The blue line is 0 here. And along here, right, sigma 2 should be exactly the same as the tension test, right? Because when you carry out a tension test, you want the stress to be uniform. And it's almost uniform until this point, right, when there's a curvature. And then you can see that sigma 2 start to vary along this line, right? Okay. Now let's look at what happens in this box, right, which I indicated in here, right? So along this box, there's shear stresses, which you can see, right? Sigma 1, 2, right? The shear stress is only 0 at this point, right? Which has to be because it's a symmetry point. But it starts to increase as you go towards the edge, or the magnitude starts to increase as you go towards the edge, right? Which basically means that most of the shear stresses are concentrated at the edge. And you can see that most of the normal stress is also concentrated at the edge, right? Of course, when I draw my free body diagram, I don't know what the magnitudes are. I'm just guessing, but I know that they have to be there, right? So here near the edge, this has to be very large, right? Okay. So the finite elements calculation will only tell you exactly what you need to know, except near the corner, right? Okay. Except in the corner, your finite element calculation is going to break down. Because if you one thing that you have to check is you refine your mesh, does it converge, right? You keep refining your mesh, and you keep seeing slight differences in solution as you get closer and closer to the edge. Okay, so that information tells you that there's some problem at the edge. Okay, you can get fairly close to the edge, but not infinitely close. Okay, right? So the question is, what happened at the corner? So what you can do in mechanics is that you can perform a local analysis at the corner. You want to ask yourself, well, so I'm rotating the diagram, excuse me. So I'm looking at this corner, and I'm putting a local polar coordinate system in here, r theta. And I want to understand what happened in the corner. Okay? So now, of course, I'm not going to go through your calculation. So if you use linear plane stress theory, the prediction is that the stress field and the strain field are singular at the corner. And it has a power law singularity where lambda is a number between 0 and 1. So if it is between 0 and 1, that means lambda minus 1 is going to be negative. That means that this is r to some negative power. So as you approach r go to 0, the stress is going to blow up. Okay, that's what the linear theory will predict. Now, of course, nothing blows up in real life. Okay, so that basically means that your theory is going to break down. But of course, the computer doesn't know that because you program it using some model, and it just obeys that model. And if you start blowing up, your computer will give up, right? Okay. So what does lambda depends on? Okay. So lambda is what is called a wedge stress intensity factor. So in this particular problem, using a scaling concept, you can show that it has to be given by this relationship where sigma is the stress far away, which we know, and W is the width, and beta here is a numerical constant because we are doing scaling analysis, so it has to be there. Okay, and for an incompressible material, so this so-called singularity index will depend on the material property and the angle. So it depends on this angle. So in our case, this angle is pi over 2. It's 90 degrees. So for pi over 2, you have to solve for the roots of this equation. And if you solve it, it will be like 0.6, okay, or 0.64 or something like that, when the Poisson ratio is equal to 1/2. Okay, so that kind of tells us that we know, okay, from the linear analysis, that near the corner, the stress is going to be very high. So we have to be very careful. Okay, so that's the reason why a designer, if you want to be really safe, you want to round the corners. What is z? Z is lambda of the root of these equations, right? So when you write an equation, you don't want to put lambda there because then you do not, lambda is z is an independent variable, and you're finding the root of this equation, and the root of this equation is lambda. Okay. Right? Okay? Yes.
And a different question from the previous slide.
Yeah. Yes.
I just want to know, is there some scaling argument for what the length scale is over which the clamping effects die down?
Oh yeah, it's on the order of W.
On the order of W?
Yeah, right. 1W.
Nothing independent then?
Because there's only length scale in the problem. L over W is very large, right? Okay. So the only relevant length scale in the problem is W. Okay. So that's the reason why if in testing of metals, okay, people will use there's an ASTM standard, okay, and what you will use is that you will use something like this, right? They would actually give you something like this, and then you have a gauge length here, right? Okay. So they do this so as to make sure that if you do this in your experiment, which is what many of us do, right? Just put a rectangular sheet in there and then load it. Sometimes it would break at the edge when you put too much strain, right? So this is an experience we all have, and there's a reason for it, obviously. Okay. I think I see another hand earlier.
Come back to an undeformed configuration this time.
This is linear theory, so we do not distinguish between the two configurations at this point. Okay, right?
What sort of material are we considering?
Linear theory doesn't care what material, as long as it is elastic. Of course, we're always considering elastic material. So if you want to consider elastic plastic material, then you'll have a different singularity because near the edge, it yields. And now you have to ask yourself whether the material hardened or not, and so on. Okay? But this is a linear isotropic elastic solid. Okay? Okay. So I'm not going to talk about case 3 yet. Okay? So in case 3, we have the so-called pure shear test, right? So again, when we analyze pure shear test, we are assuming that this dimension L is much, much smaller than W, okay? So that's the standard assumption, okay? And that's how you design your specimen. L is at maybe 10 times, 1/10 of W, okay? And you load this, okay? And you clamp this between 2 rigid plates, okay? Hopefully you clamp it well, and then you pull it up, right? Now, of course, you will have the same problem at the corners, right? So, but let's say that, well, we know that the corner doesn't really matter if we make it long enough, okay? So hopefully it doesn't affect most of the stress field. Sometimes it does, but we'll talk about that later, okay? So again, just to get our experience, we want to draw a free body diagram, okay? So if I draw a free body diagram, I know that there will be stress in here. Now, I know that at the center, right, is a point of symmetry. So it's exactly 0, the shear stress. Well, so why shouldn't I put 0 shear stresses everywhere except at the center, right? Okay. So why shouldn't I gradually put the shear stresses here? So because this thing here is very long, and when the thing is very long, it's very hard to distinguish where the center is, right? So you can say that this is the center, this is the center, as long as you're one distance away, as long as you're a few distance L away from the edge. Everywhere is the center. That's what you assume, right? So sometimes your assumption could be wrong, but this assumption turns out to be good for this case, all right? So now, okay, so now everywhere is this, but when you get close to the edge, well, because you're claiming this, right, on here, and when you do a test, this guy here will want to come in because of Poisson ratio effect, but it can't come in because you're gluing it to the rigid support, right? So as a result, there will be a, there will be a sideways force, there will be a shear force acting in this direction. In reality, this shear force is distributed near the edge, just like what I did last time. Okay? So what happens is that if you look at this shear force, far away, this shear force will appear as a uniform stress, okay? Sigma 1, 1 in this direction, right? Okay? So now after we understand this, we say, okay, we have a picture of what the stress field is going to be like, okay? So now we can do some analysis, okay? Again, I'm assuming small strain at this point, okay? We can do the analysis in large strain, okay? So what we are saying is that because of this constraint, and because L is much, much smaller than L, there is no deformation in this direction, because everything is constrained in the one direction. So epsilon 1, 1 is equal to 0, okay? So according to generalized Hooke's law, sigma 1, 1 over E minus the Poisson ratio is 1/2, so I just take nu equal to 1/2 here, E. Sigma 3, 3 is 0 because of plane stress. This is a very thin sheet. And sigma 2, 2. Now from this, I get sigma 1, 1 is equal to sigma 2, 2, right? And the other equation, I'm imposing the strain in here, right? Or the displacement in here. So the strain is just 2 times the displacement, because I'm up and down, divided by the length, right? And that's equal to sigma 2, 2E minus the Poisson ratio, this guy, right? So from these 2 equations, I can get, 2 equations, 2 unknown, I can calculate the normal stress, sigma 2, 2, right? You notice that sigma 2, 2 is not E times epsilon, right? It is bigger than E times epsilon because of the constraint, right? It's harder to move it up, right? But sigma 1, 1 is not 0, because if you say the strain is 0, therefore the stress is 0, that would be nonsensical, because sigma 1, 1 is actually pretty big. It's about 1/2 the size of sigma 2, 2, right? Okay. Yes?
Why is epsilon 1, 1 equal to 0?
I beg your pardon?
Why is epsilon 1, 1 equal to 0?
Why is sigma 1, 1
Epsilon 1, 1. Epsilon
1,
1, 1.
1? Because this is a very long sheet, right? This is very long, and L is very small, right? Compared with the width, right? So, and this is bonded. These 2 sides are bonded. So you cannot move in, right? So the only thing that it can move in is towards the edge. But there's no edge in this calculation. Is that clear? Okay? Okay. So let's do a finite element calculation just to check, right? Okay. So again, right, if I do a finite element calculation, okay, sigma 1, 2 is 0, right, on the center line. I'm looking at the center line here, right, so there cannot be any shear stress. Okay. And sigma 1, 1, right, is sigma 1, 1 is exactly 1/2 sigma 2, 2, right? Okay. So in here, I'm staying away from the edge. Okay. So there's no edge effect here. Now in here, right, so this verified the analysis. In here, I am looking at, I'm going into this direction, right, and I'm moving towards the edge. You can see that all the stresses are practically uniform. Sigma 1, 2 is exactly 0, right? Okay, until you get to the edge, right? And remember, this is normalized by W, right? Sorry, this should be normalized by W. So when you're close enough to the edge, right? Okay, right? Then you get this effect. Yes, okay? You get this singularity. So this is the same singularity as we have seen in the last slide, but the beta will be different, right? Okay, because it's a different type of loading. Okay, so you can see that. Okay, the intermediate case, when we have just a square plate, you would think that's easy, but it's not. There's no solution for it. You have to do a finite element calculation. There's no estimate for it, right? I mean, of course, we can guess to within scaling model what the stress and strain are like, but that constant factor we cannot get, unlike the other two cases, right? That's because we don't have any very special length scale, right? So this case, there's no particular interesting length scale, right? So, and that's usually the case. When you make something that is very regular in geometry, it's actually very hard to calculate, okay? Right. So if you remember that when you read Sherlock Holmes, which is a detective thing, a story, he always said that singularity is invariably a clue. Okay? So if you have very different length scales, that the answer will be simpler. It will give you some interesting things to work on if you are fearless. Okay? So now I want you to think about this. Okay, keep it in your mind a little bit. Before, we are taking this dimension to be very thin, so we have plane stress. Now what happens if we take the same geometry, except that make it very long in that direction, okay, right? What would happen? Now there's more constraint, right? Because previously, the thing can shrink in, but now it cannot shrink in this direction and this direction. And that's what a lot of people who are interested in cavitation, like Constantino, like Kenshaw, a lot of people are interested in this geometry because it has humongous constraint, and so it can give rise to instabilities. Okay. All right. So, well, we can also do a large deformation calculation, okay? And we can do that. Again, we ignore edge effect, right? And I would like to point out that if you want to do large deformation and you want to calculate what happens near the corner, that problem is not completely resolved, because it really depends on the constitutive model. And once you go into nonlinear field theory, the singularity is much more complicated. Okay, so if you want to know a little bit more about that, I can talk to you after the lecture, but this is not the right place to talk about it. Okay, so again, now we have to go back to the model, the kinematics in this dimension. So in one direction, we don't allow it to move in, so the displacement is 0, okay? And in this direction, we allow a stretch lambda, but then the incompressibility of catalysis is 1 over lambda, so we can calculate this is a deformation gradient. The constitutive model is given by this, but we know that because we are assuming this is infinitely long, okay? So the field is homogeneous, so it satisfies the equilibrium equation identically, okay? And now we use the plane. So now the only thing that we do not know is this so-called Lagrange multiplier or pressure, and this is for any material that you like, as long as it is dependent only on I1. So it could be a Neo-Hookean material, it can strain harden, it can do all sorts of things. that, so now, but we have to enforce the fact that the our plane stress, because of plane stress, is 0. Okay. So now this equation here, right? This equation here allow us to determine the Lagrange multiplier P, and it is given by this. Okay. And now we can from this we can calculate the normal stress. Right? You substitute into this equation for the normal stress. All the other stresses components are identically 0 in this case, which you can, because the matrix has a lot of 0 in there. And this is the result, right? Okay, P22, P11. Now, it's very interesting. If you look at very large deformation, lambda, that basically means that you stretch this a lot. Well, lambda is good. Lambda minus 3 is 1 over lambda to the cube. That's going to be 0 compared with lambda. Okay? So this factor is 2 lambda times this, right? Okay. And for Neo-Hookean material, this is 2 mu. Okay, it's just 2. This is just mu. Sorry, the small strain shear model. In here, this is 2 times that, right? This term goes to 0. Okay. So if you compare P11 with P22, what will you find? P22 is now 2 times lambda. P22 over P11 for large deformation is 2 times lambda, that ratio, right? Instead of 2. Remember previously we have P22 is equal to 2 times P11, right? In fact, if you use true stress, it will be even worse. It's 2 lambda squared, okay? So basically it tells you that in large deformation, it's very, if you want to do large deformation calculation, you have to be careful not to just use the small strain theory as a guideline, because you can be off by a lot, okay? So here I just specialize this for the case of a GEN material. You can use any reasonable material you like for this calculation. Okay, so here we are back to our simple shear calculation. If you recall yesterday, Professor Kobe was looking at this problem under small deformation, right? So let's try to solve this problem using large deformation. Okay. Now, I'm doing this problem in plane strain, which is more a physical configuration. Most of the literature, they will do this problem assuming this is a very thin sheet. Okay? Now, if you have a very thin sheet, my feeling is that if you have a very thin sheet and you try to do this, it's impossible to do. It will wrinkle. Okay? It will buckle sideways and all this nonsense. So, in practice, you're much better off taking a thin sheet of this stuff, thin enough, and long in this direction, bond it to the 2 plates, and then shear it. Right? Okay? All right. So here's the geometry, which you already know. Okay? So if we assume, so now here's the problem. Because this is a plane strain calculation, is infinite in this direction, we have to assume some kinematics. Okay? So if we make the assumption of what we saw yesterday, that is, this guy here move in this direction, this guy here stay fixed, right? So every point along here, right, move exactly by the same ratio, okay? So it's become a triangle, right? So that is given by this. So the deformation gradient will now have this form, okay? Sorry, okay, I shouldn't show this. It will have this form. So x2 is the same as the coordinate in the reference configuration and deformed coordination in x1 and x2 directions are the same. x1 is this direction, right? So the only change is x1, so you get the deformation gradient like this, which is basically what, and this is true for large and small strain. So if you calculate this tensor, right, F transpose, this is what is called the left Cauchy Green tensor, because I'm going to use the true stress, okay? So now you have 1 plus gamma squared when you do this calculation. You have lambda gamma. Now, in small deformation, you throw this term away, right? Okay? And you're happy, okay? But you can imagine if this deformation is large, if gamma is large, this term actually is very important. It's much bigger than these other 2 terms, right? Okay? So just keep that in mind, okay? So now your stress, if you take a Neo-Hookean material, which is a simple material, okay? You can take any material you want. I mean, once you have this, you can calculate it. Okay, so now you don't know the pressure, right? Again, you face this problem if you have a incompressible material, and then you just The true stress is this, okay? Now you face a problem, okay? Okay, you face the following problem when you make this kinematic assumption. Well, how do you determine the pressure? Well, you say, well, I have used some boundary condition. You don't have any boundary condition to use, except you know that in here it's exposed to air. So it's traction free, yes?
Sorry, just to remind myself, once you have the deformations, the sigma is proportional to the deformation plus there is the extra pressure.
It's not proportional. What do you mean by proportional?
Sorry, it's proportional to FF transport. Plus an extra term, which is because of incompressibility.
Yes, exactly.
It's a Lagrange multiplier.
Yeah, right. Exactly. Yeah, you've got to put that term in. Right? Otherwise, bad news. Right. Okay. So we don't know this pressure. That's the problem. Okay. So now, so that's the reason why this problem is hard, because you use plane strain, and that's the reason why in all the textbooks they do plane stress. Because now the plane stress condition, just like when we do the tension bar, is going to give you the pressure. But that solution is not sensible, okay? So what I'm saying is that, okay, let's do it in this configuration. And then I found a paper by Professor Alan Jent, okay, who is a really good nonlinear elastician and a great experimentalist, right? So he suggests the following approximation. He say that, well, you know, this is traction free here, right? Okay? So here's traction free, okay? So the traction free boundary condition, if you write it out, because I know the stress tensor, I can take the dot product of the stress tensor with n, and I can assume that this face is straight, okay? Now, there's no reason why that thing is straight, okay? You don't know, okay? But let's assume that thing is straight. I can calculate the normal, okay, because I know the kinematics. I assume the kinematics. And then I can have two equations because the traction vector is in this direction, and I want this traction to be traction free. So both direction has to vanish. And now I'm in trouble. I have two equations and one unknown, right? Because I substitute this in there. I have P. I don't know P, but I have two equations. What am I supposed to do? Now, here's where Alan Jent's smartness comes in. Right? That's the difference between somebody who understands the situation and somebody who just say, oh, well, you know, I'm a tuition, I give up, okay? Right? So Alan Jent says, say, well, let's take the normal components of the traction to be 0 and forget about the other equation, okay? So then you solve for P, okay? Okay, now he get the pressure. Well, now, of course, Alan Jent, being a very careful person, is not going to stop at that, right? Because he is going to check with a finite element calculation. So, but I am being a pretty careful person myself, recheck his finite element calculation because I'm coming here to give the talk, right? So I want to make sure that it is right, okay? And it is right, okay? So this is a very good approximation, turns out, okay? So good for Alan, right? So now, after you verify it with the finite element calculation, you check, you show that for the Nilhokian material, sigma 1, remember 1 is in this direction, 2 is in this direction, and 1, 2 is this shear, right? So first of all, we have the same model, right? So remember, this model doesn't have hardening. If there's hardening, there will be more complicated exponents here. Okay, so sigma 1, 2 is equal to the small strain shear modulus times the shear strain. Doesn't matter how big or how small it is. Fantastic, okay? Good. But if you look at sigma 2, right? Sigma 2 is not 0, so that means that and it's positive, so that means that there's a normal stress here, right? So basically, in order to keep the material from shrinking, because you fix the height, right? You have to apply a tension. Your load cell will register a tension, and that tension is not small if the deformation is large. It's on the order of the Young's modulus. Now, more interesting is the lateral is the stress in this dimension, sigma 1. Sigma 1, when the strains are small, is 0, 0. 1 minus 1 is 0. So sigma 1 is 0. Great. Okay. All right. This is true. Sigma 2 is also 0 for the strains are small. Fantastic. We're back to Professor Kobe's result, right? But now, if I make gamma large, well, this look like mu times gamma square. Well, that's humongous compared with this guy, right? Okay. So because you are stretching the filaments that way, right? So there's a lot of stretching in that direction. Okay. So that's what creates this guy. Okay. So again, this is a feature of large deformation, and you can do this calculation for strain hardening material and so on, and you can check. It's still pretty good, the results. Okay. So far, I've shown you examples with more or less homogeneous fields, except near the corners, right? Okay. Near the corners, things are complicated, but away from the corners, I can use homogeneous analysis to solve the problem, right? At least approximately, okay? Now, let's look at problems that have inhomogeneous fields that you cannot escape, right, by throwing away the equilibrium equation because your fields are homogeneous. Okay, now those problems are hard, okay? And then also there are some tricky to it, okay? So so the famous problem here, right, is, I only do famous problem here. So the famous problem here is a spherical cavity under internal pressure, okay? Q, okay? I use Q because I don't want to be confused with P, right? P is the Lagrange multiplier, okay? So in here, this is a famous problem, of course not done by me. I make a little twist to it, but I'll let you know later. So in here, I have an infinite block of ideal rubber, okay? And then inside there is a spherical hole, okay? So, and let's look at what the classical linear elastic solution tells us. The linear elastic solution tells us is that at the edge of the hole, the stresses are the highest, right? Which makes sense. You basically, you have a hole in an infinite solid, and you're pressurizing it, right? The hole with pressure Q, okay? So that's the loading configuration. And what you'll find is that there's a hoop stress stretching the material, right? Because the sphere wants to expand, right? And so as the sphere expands, there will be a tension stress in the material, in this material element here. And of course, we have spherical symmetry, so it's all the material stretches the same amount. Okay? So in the classical, if you do small strain linear elasticity, the solution is very well known. And basically, this hoop stress is Q over 2, right? It's 1/2 of the pressure. So the stress concentration factor, is 1/2. Okay? So no problem. Now, if you do large strain theory using a Neo-Hookean or ideal rubber, okay, then, and remember mu is a small strain shear modulus, then the stress intensity factor or the stress concentration factor here goes to infinity, right, as Q, as the pressure approaches 5 mu over 2, okay? Or, because remember in large, mu is equals to E over 3, so it's 5/6 of the Young's modulus, okay? This is for an incompressible material, okay? So you can see that, and also, of course, because the strain, right, the hoop stress here blows up, okay? And the hoop strain also blows up, okay, right? So and in the literature, it was said that the cavity therefore can grow spontaneously if you apply too big a stress or too big a pressure. Now, of course, this assumes that the material is Neo-Hookean, right? Okay, so let's go through this problem, okay? I'll go through this problem with you, okay? So kinematics. So now we have to be completely regimented, okay? We start out with the kinematics, okay? Obviously, we don't want to use Cartesian coordinate because this problem obviously has spherical symmetry, right? A material point, right, starting at x would move to a position little x in a radial direction, okay? So because this is a vector, so we use a spherical coordinate system, right? That in that case, just like this, as you all know, okay? And spherical symmetry basically saying that after deformation, before deformation, I use the coordinate system there. After deformation, the material point, the two thetas are the same, right? Okay. The only difference is the radial vector. Okay. And now after a little bit of work, okay, and this, if you know tensor analysis, you can do it, and if you don't, you just have to work hard to get it. But I gave it to you here. So the deformation gradient in terms, remember, these vectors are still orthogonal, except they rotate. They are not fixed in space. So that's the only trick that you have to deal with. Okay. So now your deformation gradient has three terms, right? Because you are now using the symmetry of the problem. All the off-diagonal terms are 0. Okay. And you have dr over dr. That's the stretch in the radial direction. Because of symmetry, the theta direction, right, and the phi directions have the same stretch ratio, which is r over r. Little r is the deformed position of the particle, which originally at the position r, right? And from this, you can calculate your left Cauchy-Green tensor, which is given by this, okay? So this is just a standard way of doing the calculation. Okay? Now, just to give you an idea, dr over dr is easy to visualize. Little r over r is called the hoop stretch. Why is it called the hoop stretch? Because if you look at the equator of the sphere, in the beginning, the sphere has radius a, capital A. After it expands, it has radius little a. The stretch ratio, r over r, is basically the ratio of a over a, that is the ratio of the circumference, right? Because this circle here in the beginning has circumference 2 pi capital A, and later this circle has expanded to 2 pi a. Or you can do it with the area, okay? So either way, this is the line stretch in the hoop direction, okay? So now, remember that this material is incompressible, so that basically tells us that the determinant of f has to be 0, has to be 1. So that basically says that this stretch times these two stretches has to be 1, and from this you can integrate the equation, and now for any position r, from this you can calculate the radial displacement field, right? Okay? So now the radial displacement field is known. We have to calculate the pressure, because remember, we don't know the pressure in this calculation, right? There is a pressure field, right? We have no idea. Okay, so now we have to use the equilibrium equation, right? Previously you don't. Now in this case, because of spherical symmetry, there's only one equilibrium equation, and that is in the radial direction. The other two equilibrium equations are identically satisfied. Okay. Now you substitute, in order to determine the pressure, your stress tensor is given by this. Remember, right? So in here, that's the only modification I make with the standard theory in most papers, is I take this for a general material. Okay, so general in the sense that phi can be any functions of I1 that is convex. Okay, so from this I can calculate sigma r. I can calculate sigma theta, sigma phi, and it's equal to a scalar sigma. This is a tensor. This is a scalar. I should use a different notation, and forgive me for doing that, because this is not a bold face. Okay, so this is equal to minus p, and our goal is to determine this because everything is known. Okay, and I1 is given by that. Okay, so now I substitute this thing in here, right? Sigma in here is given by this, so sigma is sigma theta or sigma phi. Okay, so I substitute this equation into here, turn the crank, okay, and now here's the trick. See, remember in here, this derivative respect to the current position r, which I don't know, okay, but I change a variable because I know that r and lambda are monotonic increasing functions, right? They are dynamonotone functions of each other. So I change a variable from r, because remember r over capital R is lambda, right? So I can now change in order to integrate this equation, I change a variable to lambda, and now everything, this equation is just an ordinary differential equation in lambda, with the boundary condition that on the surface of the hole, sigma R is equal to minus the pressure, right? So now, I'm not using this little thing. So now, after I do the integration, I can integrate this equation, no problem. And now I get the relationship between my pressure and the stretch ratio on the boundary, right? Okay? Is that clear? Any questions? Okay, so all I have to do is to integrate this and I'm done. Okay? Now the problem is this integral cannot be evaluated exactly unless you have a simple work energy density function. And the simplest energy density function is the Neo-Hookean material in which phi prime is just a constant, is equal to the small strain modulus. So you can do that, okay? So if you do that, you will get this formula. This is the stretch ratio on the boundary, right? On the boundary of your hole, right? And this is your applied pressure normalized by 2 times the shear modulus. And this is the equation you can integrate exactly, so you get this equation. Now you notice that when lambda, this equation allows lambda to go to infinity. So when lambda goes to infinity, this term goes to 0, this term goes to 0, and Q over 2 mu is equals to what? 5 times mu over 2, right? Which is exactly what the blow-up stress is. Okay, so that's where the thing goes to infinity, right? Okay. Now, but here's the important part to remember. Okay, Neo-Hookean material doesn't has very bad strain hardening behavior. So it's only good for stretch on the order of 2 to 3 at the most, right? 3 is pushing it. Okay. So when you look at this result, right, when you look at this result, when the stretch is like bigger than 3, right, around here, the model basically breaks down. So you should use a material that hardens, right? Okay. So if you use a material that hardens, okay, then this integral, actually, this material here, right, is going to be a monotone function of S, right? So now, any small amount of hardening will destroy this. In other words, any small hardening this curve will not go to infinity but bounded. Okay? So you do not have this peculiarity of blowing up. Okay? Right? Okay. So and you can check me on that. Okay? Right. So now the oh sorry, I didn't blank this out, but I hope Matthieu doesn't mind. Okay. So I'll mention him. Okay. This is just to remind me to mention him. All right. So instability in confined layers. Now, if you recall, Professor Ken Shaw and actually Constantino actually did quite a bit of experiment using this confined test. Okay? So what is it about? Okay. So, and actually recently I discovered I have worked on this a little bit with them. So recently I discovered some new literature on it, and I was quite excited about it because it reminded me of what I did 20 years ago, and so it's nice to see the same thing. Somebody do a better job. Okay, so here is what it is. You take 2 parallel plates with a thin circular disc. You bond it to the 2 circular plates perfectly bonded, and then you push them up. Right. So that's exactly the same as our previous question that I asked. If you have a thin sheet and you have a lot of constraint, and you try to pull it up, what happens? Okay. So this is not just a speculation, okay? And they actually did very careful experiments with this. So what they find is that they define a ratio called D over H, right? So if you have a lot of constraint, then D over H is very large, right? Okay, if you have very small amount of constraint, right, then D over H is small, okay? So what they observe is that when D over H is quite large, you have what is called fingering instabilities. Fingers start to come in from the outside, right? And you have fingers coming in. Okay? And if D over H is relatively small, right? Okay, then there's no instability on the, if you stretch it a lot, there's nothing happening in here, they're pretty straight, but near the edge, near where the adhesion occur with the plate, you can see that there's some fringe instability occurring, okay? And then if you have very, very large aspect ratio, then you have cavitation, okay? And of course, I mentioned Matthias because he is interested in this problem, and he will talk about this, okay? All right, so this is the fingerling instability which they observed, right, okay? And this is the fringe instability which they also observed, right? So these are real pictures in here, right? This is not a real picture, this is a simulation. These are the pictures, right, okay? All right, so I think they did it on a gel, okay, elastic gel. All right, so now the same authors in 201 earlier, they did a similar experiment, except they used this configuration, which is the configuration I asked you earlier to think about, right? So again, L and W, this L is very long in this direction, so it's almost plane strain, right? So L over W is very long, and L over H is very large, right? So this is exactly the same problem I asked you earlier, okay? Right? So that's the reason why I was so excited seeing this paper, because I wanted to come here to give this example, and I don't know whether such an experiment exists, okay? So again, when this is large, right? Large aspect ratio, W over H is very large, you see this fingering instability, okay? When W over H is relatively small, right, you see, again, the so-called fringe instability that you see here, and in this case, it happens along this edge, right, okay? Y is this direction, right, okay? So this is a very complex problem, obviously, right? Okay, and the reason it's complex is because there is instability involved. So there are multiple solutions that can exist in the partial differential equation. That's the reason why that's the big difference between linear theory and nonlinear theory, right? So in linear theory, you generally have unique solution. Okay, so when you find a solution, you're happy. But in nonlinear theory, a lot of times you can have multiple states. Okay, so your original solution may have energy that is too high, and from an energetic point of view, it become unstable, and then we'll go to a different solution. And this is exactly what happened here. Okay, but to understand this, there's a simple picture that I'd like you to remember. Okay, and this is something that Ken Shaw and other people understand, but they explain it in words, but here I'm explaining it in mathematical language. Okay? So here's what it is. So let's do the problem in a little bit differently. Let's think of a fully constrained material. Okay? If I'm fully constrained, I can move in an iota, right? So what I'm going to do is that I'm going to say that, okay, I'm going to move in an iota by putting a little bit of compressibility in the calculation. So I will put a little bit of compressibility in the calculation by assuming a strain energy density function that has compressibility, and this is the standard model, okay? A standard model. It's a compressible Neo-Hookean material. Then I can calculate the energy density for homogeneous deformation, because the homogeneous deformation state does exist for this problem. So the energy density I calculated is mu, which is a small strain modulus, times beta. Beta is this parameter. Nu is the small strain Poisson ratio. You notice that when nu is equal to 1/2, which is incompressible limit, beta goes to infinity. So basically, the energy density for the fully constrained case, which is the case where W and L goes to infinity, is infinite. If beta goes to nu goes to 1/2, that basically means that you cannot do the experiments. Okay. Right? Now, but what happens if I loosen up some constraint? That is, I make this dimension W small. Okay. So I have a plane stress calculation. Well, then all of a sudden, my energy density goes to this, which is bounded, Okay? So in other words, that's the reason why the fingers want to occur. Because the finger want to relax the lateral constraint. When it propagates, it goes from plane strain to plane stress, and it decreases the energy. Now, of course, this is a very simple picture, because when the fingers occur, it also causes some localization of strain energy too, because the fingers are funny things, right? Okay? They are stress concentrators too. So you're trading. There's a trading between the two. Okay?
Excuse me?
Yes?
I'm not sure I understand how you take adhesion into account, because if you're assuming to meet adhesion, I don't get how you could have fingering. Like, do you need to take into account something?
No, there's no debonding. There's no debonding in this calculation. So in other words, in experiments, everything is stick to the surface. Okay, I mean you can see from here, right? So let me show you the experiment. I mean, you cannot argue with the experiment, right? Right? So you can see that it comes in, right? It's a purely deformation, right? So you may think that it has to come in like this, right? But no, it can break up. It's a purely elastic deformation. Okay. So instead of coming in all together, they say, oh no, I don't like all together, because all together the energy penalty is too large, right? Just like what I showed. If I break them up into fingers, then I relax the constraint in this direction, right? I relax the hydrostatic part of the pressure, right? So yes, I have to pay a penalty for having a finger, right? For having this, and I have to pay a penalty for generating more surface, which is not in the calculation. But I pay less, but my energy goes down, because now there's nothing to stop me from expanding sideways. You see? Okay. All right. So, okay. So I was quite happy with this with their experiments, and they have beautiful model. Okay. But this is just a simple-minded explanation, which hopefully help you. Okay. So now I want to show you their theory. Okay. So their theory is based on energy minimization, and it's based on the approach that any plane sections in here remain plane during deformation. Now that's an approximation, and this is a good approximation except at the edge, right? Remember edge effect. When you're at the edge, at the corners there's a singularity, and you cannot destroy that. I mean, you cannot avoid that. Okay. So this is their experiment, right? In their experiments, they load. They find this peak, and what they observe is that the fingerings start at the peak, right? Okay, and you can see this is the aspect ratio. They have different aspect ratio. This is 8, right? This is aspect ratio equal to 8, and they go down in aspect ratio. You go down in aspect ratio. At some point, you lose the peak, right? But then you still see fringe instabilities, and those are marked by this point. Okay. So these are purely experimental results. Okay? Now, as I said, once you get to the peak, the solution becomes not very useful. Okay, right? Now because it starts to bifurcate. Now, so in any case, they do a simulation based on energy minimization, based on plane sections remain plane, and they discover, and they say, okay, well, my solution. This is where the solution is good, right? That's the upper bound for undulating instability. So they draw a line through here, right? And they draw a line through here for the experiment. And this is their simulation. Now, using this, it's perfectly good simulation. There's nothing wrong with it, because simulation you can make approximations. You have to, right? The experiment is the experiment. So you notice that the simulation result a little bit high, right? So this is about 7.75. This is 8.5, right, and so on, right? They look high. So I was reading the paper, right, before I come, and all of a sudden an idea struck me that I can do a little bit better. Okay. In other words, what I mean by a little bit better is that I can find an exact solution for this problem using their approximation. So I get really excited, and then I stay up for a couple of days, and then I work out the solution. So I'm excited. I'm happy to share it with you. Okay. So here's the solution that I found. Okay, I used exactly the approximation. So I didn't change anything. The only difference is that I produced a formula that you can actually use. Okay, so this is solution, and it's too complicated to tell you what it is, but I want to show you because you can actually use it. And how do I compare my solution with their experimental data? Their experimental data is this symbols, right? Okay, and the dark line are their numerical results, which is indicated in here, right? The dark line, and the dotted line are the force calculated using this formula. It's actually not too bad, right? It's better than their calculation. But, well, of course, I mean, I use their method, okay? So it's not, I copy their idea, all right? Okay? So I have to thank my student. She just sent me this graph this morning. So, because when I left, I did all these calculations. I just say, if you have time, please get their paper, plot everything, let me know whether I get it right or wrong. Okay, I'm interested in it. And he showed me this graph, and I think it was pretty good. So I show you the result. If it is bad, I probably won't show you. All right. Okay, I'll stop here. Okay, and I'm happy to entertain questions. All right. Okay, that's it.